Going back to Mathematica, I have posted a few exercises on the web page, and of course I don't have them here. Anyway, on the web page I put six exercises for you to get some practice with Mathematica. I will assign the next homework on Tuesday. So next Thursday we can look at these problems. This is just for fun. If you don't want to look at them, it's okay. It's for basically it's to help you guys to get into the spirit of Mathematica. Then, before we start with today's lecture, I just want to show a couple of mistakes or a couple of I want to make a couple of corrections. I told you that the successive replacement, so A plus B, we replace A into C, and then we replace B into C. Of course, that goes to 2C, and I told you that there was an alternative syntax for that. Okay, it's not true, so in case you remember, please forget it, and if you don't remember, it's even better. Well, of course, not this. Okay, so I said that these are equivalent. Instead, if you do this, the first replacement rule is completely ignored. So don't just forget about it, okay? I removed that from the notebook. Second question came up last time, and it was, what if I define my function like this? Which is perfectly fine. Now I say f of 3 is 9, f of 5 is 25. So the question was, what's the point in using a delayed assignment? That's a very pertinent question. The problem is, if by any chance at some point in the program you say that x equals 6, okay, then you evaluate your function, maybe you change it or maybe you just evaluate it again, it doesn't matter. Now everything is 36 because the x at this point is not bound to the pattern, but it's bound to the global x. It's evaluated once and it's stored in memory, so at this point, doesn't matter what you pass, it's always going to be 36. I didn't want to present this because I've seen many people programming like this, just working on symbolic variables. Yeah, it's a really bad idea, so I didn't even want to show it to you, but maybe it's better to show that this is not the right way to do it. Okay, enough of that.
Is there scoping in Mathematica?
Sorry?
Is there scoping? So because in our programming languages, it would be, the text would be bound to patterns.
Yeah, not in this particular case, unfortunately. The two things are not bound to each other. Yeah. And for today, we have to do a little bit of number crunching, and then I guess I'll ask you what to do. Okay, so let's do a little bit of arithmetic, then you decide. So I want to start MATLAB first. MATLAB. What do we want to do? We want to, yeah, that's why I wanted MATLAB. Let's start MATLAB first. So we want to calculate the following function. We take a number x, we apply the square root to this number n consecutive times, so square root of square root of square root of square root, we get to a point, and then we go back by squaring, square, 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 square. And basically, we would like to have the identity function. Then we have a second function that starts from a number and goes square, 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 and then goes back square root, square root, square root. And now we compare the two of them in MATLAB, and we see how that work. Then we see how they work in Mathematica. So edit. No. SQRT. So SQRT means that I take the square roots first and then I square the result. So what I do, I start from a number and then I apply the square root 20 times. I loop square root, square root, square root. Once I'm done, I do square, 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 and I return. And by contrast, I have SQRT SQ, which instead we have the square first, so we square, we square, we square, and then square roots, square roots, square roots. Okay, let's try this out. What can we do? For instance, we can do a square root of 1.1. Right. Square. Okay. Okay. What do we expect? We would like to have 1.1, 1.1. Okay? What do we get? 1.1 and infinity. I don't like that. Format long E. Okay. Can you guys argue? Can you guys explain this behavior? Yeah.
When we do a square all the time, so in the second case,
Yeah.
we will cut a lot of values in the end.
Mm-hmm.
And then if we do a square root from this cut value, then we will come to a totally different value, but for infinite,
Wait, this is infinite. What you described that you do square, 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 that's the one.
Yeah, but then didn't we take the square root of them?
Yes. Here we do first 20 squares and then 20 square roots, and here vice versa.
Maybe just 1.1 to the power of 20 is too large number. So then it becomes inf, and then square rooting inf doesn't change anything?
That's exactly what it happens. Even though I don't think we're doing square to the power of 20. We do to the power of 2 to the power of 2 20 times, which is much bigger than to the power of 20 is. Yeah. And that's exactly what happens. So by squaring, we go to an overflow, to a number that is larger than the largest number representable. At that point, it doesn't matter if we square root or we do whatever else, we just stay in overflow, in infinite. But I told you there are many, many, many more floating point numbers close to 0 than in anywhere else. So we can easily take 20 square roots and we have still a meaningful number, and then we go back with 20 squares. Okay, let's try this one. Is this surprising? Not, right? Because now we are between a 0 and 1, and so it's exactly the same story. By squaring, now we're going down. We're going too much down, so we're going in a underflow, and at that point we just stay at 0. And over there instead we're going towards 1, because we are squaring a number that is less than 1, so we're going towards 1, and then we go backwards. Okay, and now if we go to, let's try this. Okay, so no surprises there. Now if we change this to 30, Actually, in this particular case, switching to 30, it's not going to change anything because it didn't work already for 20, so for sure it's not going to work for 30. We can look at this. I put this back to 20. And okay, you see that the rubbish, it's actually coming closer and closer to the significant digit. We're losing more and more accuracy. Again, we're losing accuracy. And you can continue the game. I think something else that I want to show you is that even if we go for an integer, we still get this kind of accuracy problems. In fact, we go to overflow, no difference. Same story if we go for a constant. Let's do this. Minus pi over pi. So we have lost half of the accuracy. Out of the 16 digits, 8 of them are gone. Okay? Okay, now we do the same game. We play the same game Mathematica. First of all, we don't use for loops because it's Mathematica. And if you submit an assignment with a for loop, you piss me off. And if you piss me off, your grade goes down. So we don't use for loops. Instead, we use nest. What does nest do? We saw nest already. It takes a function, a starting point, and it applies the function n times to that starting point. So we start from x, we apply n square roots, and then we apply pure function, oh, that's a square function, n times. And over here, vice versa, square first and square root after. Then we play with the number of evaluations, so how large is n? We can start from 20. What do we do here? We plot a number, we apply the square root function, square root square function, actually square square root, here the square root square, to a number of test points, okay? I clear t so that I'm sure it's a symbol. And, of course, I want you guys to predict what is going to come out. First of all, 1, 2, 3, 4, 5, 6, 7. Damn, 1, 2, 3, 4, 5, 6, 7, 8. Most likely, we're going to have an 8 by 3 matrix. First column will be these entries. Second column will be the result of squares of square roots. Third column, square roots of squares. So, what's going to be the first column? The first row.
It's the same that we have here, so it's t pi 1 over 2.
Spoke too fast. Spoke too fast.
Oh, sorry, yeah.
Where should I be? Here. We have a list of 8. For each entry, we will create 3 entries. So we will have an 8 by 3. Okay? And I'm asking you guys to predict the first row. Well, I can tell you this is going to be t, this is going to be pi, 1/2, and so on. I have seen there is a mistake already. Okay, how about here?
One half.
1/2 here too? Okay, let me stop here. So let's, otherwise it becomes a speculation. So let's see what these three first numbers do. Yeah, that's what they do if you don't evaluate the functions. Look at this number here. Can anyone see what's happening? Is there any mathematician here?
No, this is T by itself.
It's not quite. Look. Actually, I'm gonna make a mistake. Yeah, let's put a T here. Okay. So if we square root first and we raise to the second power, it's fine. But what about... you agree? We don't know, right, that is T. It could be plus or minus T.
Isn't it smart enough to say it is abs of T?
No, it doesn't.
Okay, T could be...
It's not abs of T, only if it's a real number. But this is a symbol. You cannot say that. If it's a complex number, it would be something else, right? So it's smart enough not to evaluate it and to leave it like this. And for the rest, you guys are absolutely correct. So far, so good. What's going to happen next? Now we have 0.5. Is 0.5 the same as 1.2, 1 over 2? No, yes, nobody believes that. Very good, I like this class. So this is going to be something but not 0.5, right? And probably the same here. We will see what this is. How about 1.0? Will we get something that is not 1.0?
But there should be 1.0 always.
Why?
Because squaring this or taking the square root always returns 1. Exactly.
Precisely. There is no approximation. Square root of 1 is 1. Square of 1 is still 1. So I hope it's going to stay the same. 1.1, of course, it's a completely different story. Then we go to 2.
Yeah, 2 and 2 equals each other. So it should be 10, right?
Yeah. Plus, we have seen that works for 1/2, so why shouldn't it work for 2? Sure. 2 dot, by now we know that 2 dot is not the same as 2, so it's going to be something else. Let's see if our prediction is correct. Okay, so 1/2, 1/2, 0.5. Ah, okay. This seems very accurate. 1, we predicted that. 2, we predicted that. 1.1, there is something, some rubbish here, some rubbish down here. 2, rubbish, and over here it seems perfect. Now I want to show you something. Let's compare these numbers with MATLAB. Let's move come on, let's move MATLAB here. Let's try MATLAB with 0.5. Is it? Oh, it's 30, right? 3788, 378855. It's absolutely identical here. Is this surprising? We have two different languages. We have the exact same result. It shouldn't come as a surprise because in both cases we are in floating point arithmetic, just straight plain floating point arithmetic. This is the standard, so the programs are not doing anything fancy on top of that, and that's the result.
Is square root really exactly specified? So how to compute the square root?
The square root is one of the functions, plus minus division times and the square root, for which the standard tells you what needs to come out in relative error, of course. But notice that the processor is the same, and all of this is implemented by the processor in hardware.
Because you could maybe do something fancy with square root by approximating it
Mhm.
or something. But it's the same answer.
So far so good. Let's look at maybe 1.1. 6484. Look at that. Absolutely identical. Now, the funny thing is that on this other column, things are not the same at all. So over here we get 0. Over here we get the exact result. So what happens is that Mathematica realizes that it's going in overflow, and at that point switches arithmetic and says, okay, wait a second, before I just give up, because overflow, you see what happens. It returns infinite or 0, so it's basically giving up the computation. Instead of giving up, switches, changes mode, and that's what we get. It doesn't always work. So let's now move to 30. And now there are overflows and underflows, even where you wouldn't expect, actually. There is an underflow here. There is an underflow here. Okay, if it's here, clearly you expect that over here too. There is an overflow over here. Basically, we have done something so gigantic, you see, we are elevating to this power, that even an integer actually goes out of the boundary. So we get an overflow. Yeah?
You said Mathematica is changing mode.
Yeah.
What's the second mode?
Okay, very good question. I'll show you right away. Let's look at the accuracy of these numbers. So instead of, let's take this table, let's modify it a little bit. So let's forget about this part. And instead of computing that, let's compute so the relative error. Okay, see how many digits we have lost. So now let me try this. I tell Mathematica to use many more digits. Yeah, 1 second. Look at that. Now I have gained accuracy. So, moral of the story. Well, let me take the question and then I tell you the moral of the story.
2 to the 30 should be on the order of like 500 megabytes to represent. So, can it be that Mathematica actually would evaluate that in a 64-bit version of a machine that has enough memory, or is this some sort of
I don't know, but it's a fair question. I remember that back in the days when 16 megabytes of memory was like, whoa, the computation was very much bounded, limited by the amount of memory that you had. So my professor back in at the university was bragging because he had 64 megabytes and none of the students had 64 megabytes, and so he could do longer, he could use a better accuracy. So it might very well be, but I don't have a straight answer. Okay, what's the moral of this story? In Mathematica there are at least 3 different types of computations. Let's say that if we stick to new numbers, then we really have 3 different types. One is integers or ratio of integers. Second mode, so there is no approximation, we are working with just integers. Second mode is the standard floating point arithmetic as the IEEE dictates. And the third mode is the extended precision, not extended precision as in we have quads, extended precision as in we have as many digits as we tell Mathematica to use. This number here, I don't know how many digits it has. It's not evaluated in a double precision or quad precision. It's just a number with those many digits, and the calculation is performed with that many digits. So if I keep adding zeros, I get something that is more and more accurate. Okay? At that point, we don't have a floating point number anymore. Floating point arithmetic anymore. At that point, all the computations are performed with numbers that are that long. So it's going to be much, much slower, but of course you gain in accuracy. And now I will show you how these 3 different modes interact, well, not interact, act with these other examples. Do you have questions so far? Yes?
With regards to the square root of the square of an integer, I'm just wondering why that isn't left in the square root form as with t, for example. Why is that evaluated?
Are you asking, let's see, are you asking this?
Yes, so in regards when you give an integer instead of t, how come it doesn't leave it in that square root form?
Where do you see that it... you mean here?
Even when it's not in the overflow or underflow mode, it will still output 2 and not square root of...
Is it? But when it's an integer, for integers, this is an equality. For integers, the square root... I see what you're saying. I guess that's the definition of square root. Give the square root of z, so... I guess it tells you what it does. So square root is not automatically converted to z, but I guess for integers it does. Yeah, that's a good point. I didn't...
Integers are evaluated before the square is evaluated before it's passed to the square root, so it doesn't even know that it once was squared.
Well, it's the same. The square root of 4 could be minus 2, right?
No, you're evaluating the square root.
Yeah, which is positive. Yeah, you're right.
Minus 2 and
I
square that, and then the square root could arguably be minus 2.
Square root of 4. Square root of 4 is 2. That's right. The square root is always positive. Yeah. Yeah.
But we can tell Mathematica that the variable we passed in is of a certain type, like integer, and then it can simplify.
You can do that. I'm not sure how to do that.
Okay.
Sorry if I didn't answer properly that one. Let's go here. Do you have other questions? Okay, let's do some calculations. So now we start with an exact number. It's the ratio between 2 long integers. Okay. Over here is the ratio between an integer and some symbol, some symbolic expression. Okay, this is the generalization of the factorial. So if you have a factorial of a non-integer, that's the gamma function. Okay, so you can do all of these things. And notice that there is no approximation so far. If you know what the zeta function is, it's the Riemann zeta function. So the question is if it has, there is the famous hypothesis, and whether all the zeros are aligned along a certain line, and these would be the zeros, and of course it doesn't, the conjecture has not been proven. Okay, so you can do all of these things without any approximation. You just work with your integers and symbols. Let's look at this number here. Again, it's a big number, but it's not approximated. So you just get some unreadable expression. And if you want a number, if you want a numeric evaluation of that, you just use n. And the question now is, yes, but this is the exact number. So PA is the precise, the accurate, the exact value, and now num A, numerical of A, it's just some evaluation of that. And how accurate is num A? So in order to evaluate the accuracy, we always do the same thing. What do you guys think we will get here? You have all the elements to predict the output. 1 would be really bad.
Something on the order of 10 to the minus 16.
10 to the minus 16 is pretty good, yes. So it will be something of the order of 10 to the minus 16. Why? P of A is an exact number, no approximation done, but numerical of A, num A, is something that is represented in floating point arithmetic, so with our 16 digits. Then the difference will be something of that order. Okay? Very good.
Mathematica convert the exact number to float to do to
Say it again.
why doesn't it it seems okay, there's num A, that's the float number.
Yeah.
Does it convert it to high precision to match it with the precision of PA, because PA is
No, that's exactly what I'm showing. Num A, it's converted, is a floating point number. It's not of high precision, it's just a double.
but should PA be converted to the same double?
Oh, no. No, because this is exact. So fortunately, you can perform this expression and get something that is even more accurate. Yeah.
So num A is converted to a big integer or double decimal type.
I'm not sure which one. But now the question is, what if I want a num A that is more accurate than just 2 16 digits? So can I just do this? I take PA and now I execute it. I extract 40 digits. Okay? Remember, this is exact, and now I want to extract 40 digits. Now I have 40 digits. Now we do this. Oh, look at that. And now I have 40 digits of accuracy. So, yeah.
This 0 times 10 to the minus 40, does this mean this number is really 0?
No. It's a 0 dot. It means that the significant digit, the most significant digit, is a 0. It means that the first 40 digits are 0 and then garbage starts. Okay, so I have gained my required accuracy. And now I'll show you a little bit more complicated example. I have some complex numbers, okay? And I want 35 digits of accuracy out of that. Okay, very good. And now I check whether I do get 35 digits of accuracy, and life is beautiful. Okay. So you got the idea. Now we go to approximations. So before I had 2 to the power of minus 2000, now I have a real number to the power of 2000, or minus 2000. And it's a very, very small number. But you see the difference, right? Before we had a fraction, now we have something that is not a fraction. Okay, now I take the first 40 digits. You see a mismatch here? See what just happened? So I asked the Mathematica to extract the first 40 digits out of this. Then I compared not with XPay, okay? I compared with PA because that's the actual exact number. And it turns out that I only have 16 digits of accuracy. Where is the trick? This number here to begin with only has 16 digits, okay? So I asked to extract 40, but see, we only got 16. If you looked carefully up here, when I asked for 35, I was actually getting 35. Here I asked for 40, but I didn't get 40. Why not? Because I'm asking for more than this number has. Why not? Because this number is not exact. It's approximated to begin with. It's a floating point number. Okay. Then, yeah.
But at the first line, you could say 2.0 to the power of minus 2000 of this n, or n of this, and then with the desired precision.
You are doing what I'm about to do, yes. So, this one we have it already. So we don't need this. So that's how to do it actually. Instead of n, you should use a set precision. Now set precision will perform this operation here with 100 digits of accuracy because I tell it to use 100. Okay. Now I do my thing and oh, look at that. I get exactly 100 digits of accuracy. So of course now I can extract 40 of them, no problem. All right? Let's try to do the same in the second example. So we start similarly, we have 16 digits for the real part, 16 digits for the imaginary part. So this number again is something of the order of 10 to the minus 15, 16, that's fine. If I want 35 digits, see that I'm not getting them. So even if I ask for 35 digits, I'm stuck to 15 or 16. So now we go for the same trick as before. We evaluate the whole thing, but now with 35 digits of accuracy. Somebody's not happy already? And I still get 15. So let's look more closely into this. Why is this not working as expected?
Because you still use XP instead of the calculation of XPE.
Ah. Okay. So let's try that. That's a good point. Where is it?
In 60.
Here. 60. Yeah, thank you. Oops, that doesn't work anyway. So, let's investigate further. Look at that. That's exactly what I was doing next. If I only remembered. That was my exp-c. That's what you just suggested. So I actually get 50, but still they're not the exact ones. So now I get digits, but they're not the good ones, because as you see, the accuracy is still 10 to the minus 15. So the point is, the problem is where I am asking to set precision. Over here I have an expression first, and then I set the precision. Let's try to set the precision in the right place. So let's go inside, let's set the precision of this expression, and then let's compute the sign. Doesn't work. So, okay, let's go a little bit more inside. Let's set the precision of pi to the power of blah, and then I do plus I, and then the sign. Still doesn't work. Let's continue this game. How about I set the precision of the stupid number, and I convince Mathematica that this number has 35 digits. Look at that. Do you see what happened? For the first time now, I performed the operation not with 16, but with 35 digits. And I still lost a couple of digits in the computation. This is not 35, it's 33, but that's okay. The crucial point is to force the computation to actually be performed with as many digits, and not just to ask to get many digits of something that was never computed with so many digits to begin with. And now I can give you the same example. All right, here I constructed 3.5 with I think 35 digits, and here you go. So set accuracy is the same as building the numbers with lots and lots of zeros. Moral of the story, these two numbers are not the same at all. Okay? But funnily enough, these numbers are the same, these first two. Anything up to 16 is a something, and from 16 on, it's extended precision, completely different world. Okay. This is just for you to know. I told you many times that Mathematica is extremely powerful for symbolic computations. So you can solve an equation. Of course, now you can't because we assigned the stuff. Okay, it solves equations symbolically. For each symbolic operation, there is one or more numerical counterparts. So for solve, there is n solve. There is all this family of the n star functions, and they solve the equations not symbolically, but with numerical techniques. So the solution of that is something exact. The solution to this is an approximation. Same, you can compute the sum of that thing, and you get the exact solution. You can compute n sum, which is the same as summation, but now computed numerically. And the same story for integrate. You can compute primitives, indefinite, definite primitives, all that you want, but you can compute the actual, so this is the timing, this number here is the same as this one here, or at least 11.8 is an approximation to that expression. You see the difference in timings. Of course, this is exact, and this is a numerical integration. And so on and so forth. So here I just list other members of the n star family of functions. And that's enough for Mathematica, or at least that's enough for this notebook. So this is complete, and I put it up online. And the assignment is will be based on all of these, okay? I mean, all of these concepts, ideas from this. If you have questions so far, it's a good time to have questions. Otherwise, if you don't have questions, I ask you whether you want to go into visualization right away, or if you want to look at an application that I created for a friend of mine. It's about sound. So I show you how one would actually would go about programming in mathematics. So which one of the two, visualization or sound? Sound. There is no sound in sound, unfortunately. Actually, let me try something. What was it? I removed the sound. So, okay, here's the story. A friend of mine is a composer. He creates music for movies and TVs, movies and stuff like that. And he wanted to, he's very much into automating the generation of music. So he called me and he explained to me what the problem was. Basically, he has a piece of music, a track, that ends at a certain note, certain tone, and then after a few seconds of intermission, because the scene changes or something like this, a different piece of music starts describing a different scene of the movie. And he wanted a transition from the arrival note to tone to the starting tone of the next scene. And he says that, of course, you can transition in a linear way, like a crescendo in a linear way, but it says that that's kind of boring, because our ear doesn't like linear transitions very well, a whole lot. So he asked me to connect these two tones with some exponential curve. And he wanted to experiment with the exponentials. So not only did he want an exponential curve, he wanted to be able to control this exponential. And I'm like, okay, it's no problem. And I did all of this in Mathematica. And in fact, I was, it's possible to, with this play, I think it's play, it's possible to play tones. Let's see if I find it. So if I play sine, we need a frequency. We need a real frequency. As you can see, I didn't prepare this. Okay, let's take a frequency. Sine x. So these should be, I don't know which tone. Let's see if it's. There is.
This is about 30 hertz.
Yeah, so it's very, very low.
Or 2 pi maybe.
I should put it to a pi somewhere. It's very possible. Haha, thank you. So these are 2 seconds of some tone. Well, if you read the music, this is a sol. Let's take this. But this is a very, very low octave, probably. But let's try. We cannot hear it exactly. Let's take something. So this is a fa of the 3rd octave. We should be able to hear this. Here we go. Okay, and I created all this application starting from a certain frequency and arriving to another frequency. And I was connecting them with an exponential function. And I will show how to do all of this. And then we realized that the oscillometer, which is the thing that produces the sound, in Mathematica it is crappy. And so we basically removed the sound because it didn't matter. Anyway, he plays his own instruments. And so that the musical part doesn't even matter, but that's the background, okay? So down here we have a list of frequencies for all the tones, and this is going to be part of your assignment, by the way. You will take these as input and you will have to do some processing on these tones.
Did you give this database?
I copied from a PDF, and that's why it's so bad, and that's what you guys will have to do for your assignment to filter. So this is what the database, the list of tones, looks like. And after some maneuvering, which I keep hidden, so the maneuvering happens in here, this is what you guys have to get. So a frequency, and then the name of the, oh, by the way, maybe not all of you are familiar with this is the Latin names of the tones, and the English, British names are C, D, E, A, B, and so on, okay?
So in English it's B? Okay.
Yeah, C, B, D, E,
Because
F,
in German it's not B, it's H at the end.
all right. In my language, that's what it is like. So we stick to this. And that's what you guys have to produce. Okay, this is just a start. And then actually these are way too many notes because there are all the intermediate notes, and it didn't want so many, so we filter a little bit. So this list, all tones, is the list of tones that we will actually use. Okay, that's almost irrelevant. What do we want? We want to connect 2 points with an exponential curve. So I define an exponential curve. Unfortunately, he wanted to have control over this exponential, so I had to add some parameters. I wanted to add some freedom. So I added these 2 parameters, K1 and K2. Okay, see, so my function is a function of K, but I have 2 parameters. These parameters are like, this function is such that if I pass 0 to x, I find myself in 0. So I normalized this function to start from the origin. So basically, it doesn't matter which frequency I start, because I can always shift. My function is defined to start in 0. But now, of course, I have to arrive to the right point. This is just to avoid the funky cases. So here I evaluate the function in 0, and I want this to be 0. Here I evaluate the function in a point x1, and I want to be y1. So I want this would be the value from which I wanted to start. So, okay, I have basically to solve this equation so that in x1 I do get y1. I have too many variables. I have k1 and k2, 2 variables, so I can fix one and solve for the other. So I artificially fixed k2, here I call it t2, and b will be a parameter. So my friend will be able to change the value of t2. It doesn't matter which value it assumes. B will always be computed so that in x1 the function goes to y1. Okay, how do I do that? I basically express the parameter k1 in terms of a, b, which are the coordinates of the arrival point, and the t2, which is, as I said, a fixed parameter. And so what do I have to solve? I want f of, in the point A to be equal to b. T2 will be fixed, and T1 is what I'm trying to solve for. So I define that as a function, and let's see what comes out. Now I evaluate, oh, let me shift this. Can I shift it? No. Damage. I would like to shift it. I cannot shift it. I have to do this, sorry. So we solved, where is it? Here we go. We solved K1 as a function of the arrival point and T2. Now, what do we want to see? We want to see if this actually works. We always have to try out what we do. So now I evaluate my function in the point x1 with K1 computed as a function of x1 of the arrival point y1 and K2, which is fixed. What should I get from here? Let's see if anyone has followed me so far. This is the function that starts from 0, 0, then it's an exponential. The exponential is dictated by the arrival point, the value of the arrival point, and some K2 parameter with which I can play. What should this value be?
Y1.
Precisely, but it's not y1. Look what we get instead. Well, no big deal. Let's just ask Mathematica to simplify. Yes, indeed it is y1. So we're doing the right thing. So we are happy. So far, so good. So I can start with a plot already. I fix the arrival point. I fix this K2 parameter, can be anything. And I plot the function that goes from 0 to 3, y3, because that's x1. Actually, here I should put x1. And this is my exponential, one of the many. If I change my value 1 to 1.5, I get a different exponential. If I change it to 0.5 minus 0.5, okay? Now, just for you guys to see, this is a function. I pass a symbolic function to plot, then I tell him the range over which I want to plot, and then epilogue is the opposite of prologue. Epilogue means after you have read a book, there is the epilogue. So the epilogue is after you have plotted the function, add whatever is here. There is also the prologue, which would plot the dot before plotting the line. Okay. So these are ways of annotating, of adding graphics to a plot. And now since K2 is a parameter with which we can play, I show you this manipulate instruction, which is very, very useful. What am I doing? Manipulate allows me to put on a slider a parameter. So now I have all of the above, but notice that K2 is free, it's not bound to anything. And instead, K2 is bound to an iterator. When I evaluate this, takes a little while. Now I have the plot and the slider. The slider comes from the manipulate, okay? Here it says -5. Notice that I have added a plot label K2. So now I will have this plot title over here that shows me the value of K2. If I change the value, the exponential is automatically recomputed, and this value is shown there, so I don't need that. Here we go. And so my friend can have an idea of how the exponential varies by varying the parameter k. Okay, so far so good. I have a yes?
I think I didn't get it right. So one of the first steps you had a function with two variables, but only one equation. So you fixed one of the variables.
Yes.
So you solved the function and received the equation and received a new function. And
I didn't receive a new function. I had two variables. I wanted to solve one in terms of the other. I have an exponential with the two parameters, k1 and k2. I don't have so many constraints. My only constraint is that my function starts in 0. Okay, that's not a constraint because it's I normalize the function. Every time you're in 0, that function will be in 0. So my only constraint is that in x1 will be in y1. But I have two variables, k1 and k2. So I fix one, and I make sure that the other is chosen so that in x1 my exponential goes through y1.
So what value did you choose for fixing the one?
From what?
For what value did you choose for the one you fixed?
This is it. That's the k2. I fix that and I compute k1 as a function. Oops, before it crashes. So what's the point? What am I trying to do now? I want to split this exponential in n intervals, in n parts. Why? Because I have to put some tones, some notes in each of these intervals. So that's what I do over here. I am creating 0, 0 is my left point. This guy over here is my rightmost point minus the interval. Remember that since this is time, I don't want to play a tone right on the right boundary, because that's when the new piece of music will start. So I have to stop one step earlier, and that's the step earlier. Okay. And I have a point. All right. So now I have all my nice points. Notice that the epilogue now is a map of the point function over the list of points that I have generated. So these are the list of points. This is the list of points. And now I put the dots over here. And now I want basically my musician to play a tone at each of these intervals, points. So what do I have to do? We have to put this into context. It's true that this function is normalized to be in 0, but in practice, this will be some frequency. And that point up there will be some other frequency. And so these intermediate points will be some frequencies in between. But remember that we don't have a keyboard, we have a player with a piano or with a violin. There is a discrete number of tones that he can actually perform. So we need to go here, look at this value, and find what is the closest existing tone that he can play. And that's what we do here. We have a find tone. Basically what I do, I find the closest tone above and below the frequency, then I measure the distance and I pick the one that is closest. That's what I'm doing here. See some mapping, some selecting as an example. So I say, okay, this is the frequency that I want to, that I have to play. It corresponds to this tone here, and this is the distance between the analytical point that doesn't have a tone and the actual existing tone. So now we can put everything together, and I have this long function. What does it do? We start from one particular frequency on the left. We have an arrival frequency on the right. We have a duration. What does it mean? It tells me how long is this transition. Remember, this is an actual piece of music, or sort of, so 1 second, if we divide it into 10 parts, it means that this guy within 1 second has to play 10 notes. If you have 10 seconds and you divide it in 10 parts, it means that plays a keys, then waits 1 second, then another, then another. So duration actually makes a difference. And notes, tones is how many tones you want in between. And this is our parameter, our K2 parameter that he can play with. And if he doesn't specify it, we set it to 2.5. And what do? I show you what we do. Maybe then we go back. We say this is the starting frequency, end frequency, 2 seconds, just play 6 tones. That's K2. This is what I do. I show the starting frequency, the arriving frequency. I plot where the tones are, and I show which are the tones. How to do all of that? Okay. Now, my output is a show. Show puts together graphics. In this particular case, so I need a list of graphics. In this particular case, I have a plot, and you have seen the plot already. That's just the exponential. And then, after the plot, I have a couple of graphics. So, one is to put the points and the lines, and one is to put the text with some text style. So I have basically 4 components: the line, the points, the segments, and the text. And now we can generalize the whole thing. What is that? What is this? Why manipulate is not working with me today? Who told you that dynamic updating has been disabled? Dynamic updating, okay. So what do we have here? I have fixed the starting and the ending frequencies, and I have also fixed the duration up to 4 seconds. So now what I can play with is the shape of my exponential, and the number of tones to play. And I can see how they change. This is the boring, linear, and stuff like this. Okay. We can do even better. Here's the final product. So, my friend, since he's a composer, he doesn't really care about something like this. He wants to know when to play something and what to play. He cannot really deduce the attack time from this, so I created this table. Now we have all sorts of sliders: duration, starting frequency, arriving frequency. Well, we cannot see them, but here we have them. Okay, we can hide them. Then we play with our parameter as we change n. Patience, patience, patience. I promise this is the first time I see this happening. So fewer frequency. Okay, and you see now that the table changes, so we can play with duration. I have a question for you. As I change the duration, thank you. That's why I couldn't figure out what was happening. As I change the duration, do you see that something happened? I mean, there are changes. There are changes even in the notes, not only in the times. Do you know why?
Could you please show it again?
So let me show you. My point is, as I'm changing the duration, the notes are changing as well, the tones. You see, there are changes here?
Is there more some musical theory?
No. No musical theory.
Why wouldn't they change?
Why shouldn't they change?
Why wouldn't they?
Maybe that's a good question, but I want to trick you guys. Well, one would think I have to start here, I have to arrive here. If I just if I have a longer period of time, well, each note stays the same. It's just that each note is longer.
But they would get linear.
Precisely, it's not a linear function. We are connecting these 2 points with an exponential. So as I grow on one side, everything changes. It's really, the intuition is totally wrong. We are not in a linear world anymore. We're following an exponential path. Okay, this is it. And this is the final product. And of course, as it always happens in these kind of collaborations, they ask you to do something, you do it. The minute you have done it, they ask you something else. Because either they realize that what they asked is not what they wanted, or they saw that this is so cool, and so they want something more. And that's the second thing that happened here, the second case. So immediately he realized that even this is not so cool, because the notes, the tones are equidistant. So they are spaced in an exponential manner along the y-axis, but not along the x-axis. And so he said, oh, but if you can do that on that, then you can do it over here too. Like, sure, okay, but maybe I will let my students do it for me. So, how many of you thought that this is cool? Okay. Okay, how many of you thought that it's easy to accomplish this kind of prototyping or this kind of programming at this level without having to go to, the details of a low-level programming language? So how many thought that this is the right level of abstraction? Come on, here I want to see everyone. Even if you don't believe it, you have to make me happy. We never had to compromise. We never had to change the level of programming, the level of abstraction, because the language was forcing us to do something that could not be expressed. Remember when we were working with matrices and you guys went down to at the index level? That means that you're programming at a different level of abstraction. Over here, we never really changed the level of abstraction. Yep.
There is an experimental sort of programming language exactly for this kind of problems.
Yeah, I know.
For fun of it, I actually played around with it, so I think...
Which one? C-Sound?
I don't remember the name.
Okay.
It was a year or two ago.
I took a course on that, so I know what you're saying. There are several of those.
The right level of abstraction may be arguable in this case.
All right, anyway, this is enough. You have 6 problems for next Tuesday. No, sorry, 6 problems just to play with. On Tuesday, I will give you the assignment. There will be a challenge. In fact, there will be 2 challenges. One of the challenges will be on speed. The other one will be just purely for fun to write the shortest program that you can come up with. Again, it's purely for fun. Don't ever go out and say, oh, Biantinesi teaches us to write small programs, because that's absolutely not the point. This is just purely to have fun with this cryptic language. And then there are going to be a couple more problems, on replacement rules and mapping and functions. It will be a team assignment again, so if you want, you can start already. It's going to be 2 people. What else? I don't know. Do you guys have questions? Oh, and we will have a lecture on visualization. Again, like for MATLAB, it's not about everything in Mathematica. It's just to give you an idea of what Mathematica is good for, as opposed to what MATLAB is good for. This is it.